First up, we have Robert M. Freeland to give us a talk titled Infrastructure Development Leading to the First Long-Duration Interstellar Probe. Let me tell you a little bit about Robert. Robert earned his physics degree from University of North Carolina, Chapel Hill. Then he entered the corporate computing world with stints at Alex Brown and Express Scripts. In 1995, Robert co-founded the first company to sell insurance online. After it was acquired by Intuit, he co-founded PodTrack, the first company to sell advertising in podcasts, and now the industry's leading measurement authority. Robert joined Project Icarus in April of 2010, eventually serving as the board member and deputy project leader under 3 successive leaders. He is the primary architect behind Icarus Firefly, a published Z-pinch fusion-powered interstellar probe design. In 2017, Robert introduced and chaired the highly regarded Sagan meeting format at the Tennessee Valley Interstellar Workshop. Robert is also involved with the current Bis Space initiative at the U.S. chapter of I4IS, and he is a gentleman and a scholar. Please welcome to the stage, Robert Freeland.
Thank you, Sonny, for the great introduction. And thank you, Andrew, for organizing this thing, and to the IRG in general for putting on these great conferences. I'm going to talk today about 3 kind of related projects through the British Interplanetary Society. The first one is Project Daedalus. Of course, most of you are familiar with it. It was the first credible study for an unmanned interstellar probe. It was published in 1978. They used ICF fusion for an undecelerated flyby of Bernard's star. Then I was involved with Project Icarus, which spun up in 2005. It was envisioned as a successor to Project Daedalus. The idea was to take a look at what we could do with fusion technology using more modern technology that was available. We did adopt some more stringent requirements for that project. We were looking at a fully decelerated probe into Alpha Centauri. So we were taking 150 tons of scientific probes and stuff, fully decelerating into orbit around Alpha Centauri. And the goal was to be able to get that package there within 100 years of launch, and moreover, to launch it before the year 2100, which is where we're going with part of this talk. Then I'm also going to talk about the Bis Space Project, which is basically envisioning how humanity will expand into our solar system in the relatively near term. All right, this is Firefly, which was the Z-pinch fusion design that we published in 2015 under the Project Icarus umbrella. And I'm not going to dwell on it today because I've talked about it at previous TVIWs, so I will talk about it toward the end, though. We were just looking at a discussion of the various fusion reactions, and I don't have proton boron on here precisely because the Brimsterling is really, really devastating, but I hope we can find a way around it. Anyway, the easiest fusion reaction that most people look at is deuterium tritium, but the problem with it is it spews off these super fast neutrons, and those cause all kinds of problems. Down at the bottom is the reaction that is usually the go-to when people are designing fusion engines. They say, oh, we'll just use helium-3 because deuterium helium-3 is, well, the primary reaction at least is aneutronic. But the problem with that, of course, is, well, A, you've got side reactions that are neutronic, but also we don't actually have it here on Earth. We get a little bit when tritium decays from nuclear warheads, but that's about it. So for Project Icarus, we used deuterium-deuterium fusion, but that came with some negatives. A lot of waste energy that I just mentioned, a bunch of neutrons. If you try to shield against these, you get gamma rays. We've got Brimsterling also contributing X-rays, and shielding any sizable portion of that just adds too much mass to your spaceship. That's one of the reasons that Firefly had an open core reactor. And we let most of that radiation escape into space. So I would love to use helium-3. And the question then is, at what point will helium-3 cease to be unobtainium? All right, so it was mentioned in one of the earlier talks yesterday that there is helium-3 in the lunar regolith, but to get enough for an interstellar mission, you would need to literally process mountains of lunar regolith. So helium-3 is relatively abundant in the atmospheres of the gas giants, and so this is generally where we think we can get enough of it to do an interstellar mission. Back in 1978, the Daedalus team envisioned the solar system-wide economy that was going to have an extraction facility in the atmosphere of Jupiter, and that was where they were going to get the helium-3 for their mission. They didn't. I mean, I should say, too, the Daedalus team, the project, was really a proof of concept sort of project. It wasn't a mission plan per se, so they didn't really bother with the detail of when exactly this would be. And then, the Icarus team, we were looking more at a launch date potential, try to figure out how to do this before 2100. And we concluded, well, most of us concluded, that helium-3 was not likely to be available in sufficient quantities by this 2100 AD launch horizon. All right, so when can we get it? I'm going to kind of switch gears here and talk a little about the BIS Space Project and kind of this vision for our expansion into the solar system, because that directly relates to the helium-3 question. This is a historical population growth for the human race here on Earth. It has, over broad periods of time, been about 0.06%. That's a very, very low number, right? It peaked at just over 2% in the 1960s. And it has been in decline ever since. And right now, the projection is that by about 2100, human population growth is going to be zero, possibly even negative. And this is from the United Nations. This is kind of their projection of human population. Now, one of the early kind of motivations for human expansion into space was this Malthusian concept that we're going to run out of space on Earth. And this seems to debunk that entirely, right? I mean, what has happened is that the population has approached a asymptotically sort of a maximum, and it looks like we're going to kind of plateau out there absent anything else, right? But O'Neill came up with this idea that, he was actually motivated by the Malthusian question, but anyway, he came up with this idea that we could live in orbital habitats, and he described these. Made a case for why these are actually preferable to living on the surfaces of rocks. That's abundant mineral resources, available energy, Earth-like conditions. All of this is good. And so the first couple of papers out of the BIS Space Project before I even joined them were about kind of re-engineered O'Neill habitats, just kind of thinking about what would those look like. One of the things that we realized in the course of this project is that there's this mythology about self-sustaining colonies. I mean, they come up in science fiction all the time, but in reality, these colonies are fundamentally fragile. And the reason is because we as a species have adapted to a particular, conditions here of gravity, air, water, food, all of this stuff that we get for free living on this particular rock. And in an extraterrestrial habitat, you have to provide all of that artificially. And because it's artificial, it is fundamentally fragile. And the only way to sustain it over really long-term timeframes is to have access to that reservoir of, it's called a restorative reservoir in this Pan-Morio theory. But anyway, that is the place where these conditions exist naturally, and you can access resources and energy and people and whatever you need from that to keep your thing going. So there's a connectedness that has to occur with orbital habitats. And so if we do start moving into orbital habitats, like how many people could that be? Well, we just said Earth, maybe 10 to 12 billion. There was a paper by Mark Hemschel that suggested that Earth orbit could support maybe another 10 billion. By extension, you can get about 5 billion around Venus and Mars, maybe another 10 billion in the asteroid belt, and then possibly 15 billion each around the gas giants, around the moons. So you add all that up, you get about 100 billion people as perhaps the carrying capacity of the solar system. It's not like we're going to get there soon, but we did a little kind of guesstimate of like how long would that take. This uses a logistics function, which is, that asymptotic approach to a maximum carrying capacity. And it looks like, about 20,000 years, we could possibly saturate the solar system, maybe faster if we, grow more like we have in recent history. Of course, maybe never if we grow like we may be in 2100. So in the BIS Space Project, they imagined these 4 generations of kind of development and expansion into the solar system. And they were characterized primarily by the propulsion systems that were available to each of those. So the first one, I'll just go through these one at a time. And the dates here are, you can take different assumptions and get different dates, but I feel like these are pretty good. We're in the first generation now. We have rockets. Chemical rockets that are taking things into space. We actually have a small habitat in orbit. All of our stuff that is in orbit, though, we constructed here on Earth and we took it up, right? We assembled the ISS in space, but it was all built down here. We've been to the moon once, and there's talk about using it for resources. So in the second generation, we move into a little higher Earth orbit. We're starting to make actual use of the moon. Transport at this point could be fission powered. I know there's a lot of work that's been done on those. That's all current technology. We could build those. So the technology is really close. I put the start of that at 2050. Maybe I'm being optimistic, but seems reasonable. And then, at about 100, 150 years, we're on to the next thing, which is really expanding to Mars, Venus, all of the inner planets. And at that point, I think that the deuterium fusion-powered ships are going to be fairly readily available. I mean, the technology's there. We've had, 3 different presentations on fusion drives just this conference. And then the 4th generation is where we've expanded into the entire solar system. So sometime prior to 2500 AD is when we could conceivably have this full-scale mining operation in the atmosphere of Uranus to get the helium-3. So this is just one of the models that kind of went behind the numbers as far as the dates. You kind of have to look at the supply and the demand side for habitations in space, because like on the demand side, there's the pace of human population growth. How fast can you actually produce people who want to be in space? And then on the supply side, there's the ability to manufacture habitats. And that in turn is dependent on the ability to actually put manufacturing facilities in the places that you need to build the habitats, because you're not going to build these things. They're massive habitats. You're not going to build them on the ground and send them up. You have to build them in space. And so this just basically had an assumption that you can move to a new location every 50 years, build another one of these things. You do that, you can get to about 30 million people in space by 2500 on that. All right, so what are the implications for interstellar vessels, which is really kind of bring this back around to where I started. This is the pie graph for the mass distribution on the Firefly model that we published. And you can see we've got 25% of the mass is in the radiator itself. We've got another 20% that's in the radiator coolant. And we've got another 10% that was pumps to pump that coolant around, right? So that's half of the mass of the vessel, plus a little, that just went into the dealing with the radiators. And I mentioned before, Firefly has an open core reactor, right? I mean, so this is letting almost all of it go into space. You still have to do this, half the mass. And moreover, in order to make all this work, we went with the most exotic radiator we could come up with, which actually boils beryllium into a phase change radiator. We needed 480 tons of beryllium to do this. Total cost just of the coolant at $850 per kilogram was about $400 million. So that's an extreme design. It would work. I mean, we could do it, but it's not very economical. So what do we get with helium-3? I say here it's basically cheating. With helium-3, we can take that same model and replace 35% of the deuterium with helium-3. And our radiation output falls by 75%. and the exhaust velocity goes up. Why? Because we've got more charged particles that we can actually redirect into the exhaust. That higher exhaust velocity then allows us to reduce the mass flow rate to the drive. Don't have to push as much fuel because we're getting more out of it. Reducing the mass flow rate means you're burning less, you're producing less radiation from that. Different effect than the first one. And all of this radiation reduction then means you can reduce your radiator mass, you can use less fuel, your lower burn rates. It cycles. And then you get down to a point where we can say, all right, let's just ditch this beryllium because this is like really, really crazy, and instead use aluminum, which is a lot cheaper. It's our second best coolant. We're still boiling that off in the radiator. So, I mean, it's still running really hot, but it's a lot cooler, a lot cheaper rather. And then, of course, the physical size of the whole vessel can be reduced. Of course, also improves the efficiency. So this is just a summary of a comparison of these two models. The first one just using plain deuterium, so that's the one that we published. And then the second one is using helium-3, again at 35% concentration. And you can see here that, we've got the same time to Alpha Centauri. With terms of reference for Project Icarus, by the way, was 100 years. So that's why these sum up right there at the bottom to 100 years. So same time to destination. We've got 1/5 of the fuel, which is a big savings because that stuff's expensive. And then we've got 1/12 of the coolant, and that's even using aluminum instead of beryllium. And then burn times are reduced, and so overall it's just much cheaper. So that's a win all the way around. And so yeah, my conclusion for this is let's hurry up and get through this generation 3 so that we can get the helium-3 and do these missions. As I said in the beginning, I mean, yes, we can do them with deuterium, but this is a lot easier, a lot cheaper. This last image, by the way, is one that Michelle drew up, which is kind of an envisioning of what the helium-3 version of Firefly would look like, because it has much smaller radiators. So I'll stop there. Any questions?
We do have some time for some question.
So you spoke about going and mining existing helium-3. What are your views on making helium-3 versus, either may sound difficult, but what are your views on that?
Yeah, there are designs that have been proposed for manufacturing it, but they're not very efficient. Like, you almost have to presuppose that you have terrestrial fusion generation first, and then you're making the helium-3 as a byproduct. And even then, we're talking about tons of helium-3 that we need. And human energy usage would have to be a lot higher here on Earth for us to produce that much of it, bottom line.
Very interesting talk. Have you guys considered the impact of spin polarization on the engine? And if not, have you seen our poster on the impact of spin polarization?
So no, we haven't considered that. And yes, I have seen your poster. And so, yeah, would be interested to talk to you about that.
Wonderful.
Yeah.
I'd like to talk about the concept of the O'Neill spheres. It seems to me that there are some limiting technologies for that. And one of them is cheap lift capability. The other is cheap habitation for manufacturing and a cheap way to get back and forth. Thus, a fusion drive would open that up. Are there any other limiting technologies that you can foresee that why we can't start thinking about it today?
Yeah, so good question. One of the main ones that we've talked about in the Bis Space Project was the availability of volatiles, specifically hydrogen and nitrogen. Yes, we can extract them here from Earth to an extent until people start to say, hey, we don't want you taking our atmosphere. But then we need to start looking for extraterrestrial sources of those. And, Venus is great for that. They have everything we need in high concentrations, and they even have Earth-like conditions in the atmosphere. So that would be my preference. Yeah.
One of the critiques of Project Daedalus was that if you try to suspend a giant balloon in the atmosphere of a giant planet, you're going to have a slight difficulty with grounding because of lightning discharges. Have you ever seen any way around that in the proposals, the updated proposals to mine this stuff?
No, I have not specifically seen that. Yeah.
Plop.
Is there helium-3 in the solar wind?
There is, but again, I need tons of it. So the amount of solar wind that you'd have to intercept to do that would just be extraordinary.
But extraordinary is certainly possible.
Yes, I would say yes. So not impossible, just, it's like mining a mountain of regolith on the moon. It's just not really something that I see us doing practically. But yeah, it
Fair
could
enough.
be.
So you're saying there's a chance?
There's a chance. There is.
I just wanted to ask a question about, 100 billion people in the solar system and kind of growth mindset versus alternatives to growth mindset, and thinking about, not trying to get more people, but trying to maybe get higher quality with less people. And whether or not you could comment on that.
Yeah.
Hard
So
question.
when we did that growth picture, I'll go back to that one if I can find it real quick. The red line is basically what humanity has done on Earth. And then we also kind of suppose these two that were less rapid growth, which matches a little more what we're kind of trending toward here on Earth. And so, there's kind of a pessimistic scenario where we don't grow anymore at all, right? And one planet's just fine and we don't exploit the rest of it at all. I say pessimistic because I would like to see humanity on more than one rock. And I would like to see us at another star. So I presuppose there is some growth and then some motivation for us to keep expanding. But yeah, we've got to do it in such a way that we don't strip mine the entire solar system.
One more question.
Hey, Jacob Puckmiss from Blue Marble Space. And just to follow up on that a little bit, it's not mutually exclusive. You don't have to have this kind of growth to have humans in space. You could have sustainable growth that plateaus on Earth and still have individual missions that send humans into space, and you may still need to mine helium-3 and so forth. So I think it's not a trade-off between populating the solar system, populating the cosmos versus actually, crewed exploration. And it's not necessarily a trade-off.
Yes, but the infrastructure that's needed to do the helium-3 mining is significant. And I don't see, in the really near term that you can do that, just send a bunch of robots out there and have them send you helium-3 back. It's going to take some human presence there to manage it, I think, because things break. Oh, no. And, this graph here, that's 20,000 years out there on the end. So I'm not saying we're going to be anywhere near that before we go, but it's kind of a vision for how we get there.
All right, let's thank Robert. Great job. Great talk.